You open your browser, type in a web address, and press enter. Instantly, the page appears. It is a mundane, split-second action that we perform dozens of times a day. Because it happens so seamlessly on our screens, we tend to use the words internet and web interchangeably, though they represent two very different things. The internet is a massive, tangible network of physical hardware, cables, servers, and routers. The web is a software service that rides on top of that physical infrastructure. Let's freeze time right at that keystroke. We are going to track the invisible choreography of a single data request in the exact millisecond after you hit enter. Tracing this path reveals how a globe-spanning network of glass and copper, built for massive redundancy and scale, manages to flawlessly connect the world. When you ask for a website like youtube.com, your browser immediately hits a language barrier. Computers cannot locate a destination using human-readable words. They require exact mathematical coordinates. So your browser checks the domain name system, or DNS. This decentralized phone book translates your text URL into an IP address, a unique numeric string identifying a specific device. That IP address acts as a geographic coordinate, pointing directly to the exact physical server on the globe storing your files. With the destination set, your request leaves your device. It travels out of your home as a rapid-fire pulse of light or electricity, entering the local network of your internet service provider. If the server is located on another continent, that pulse shoots across the ocean floor through massive, heavily armored fiber optic cables. To navigate this sprawling maze of cables, the network relies on BGP, the Border Gateway Protocol. BGP is an algorithmic routing system that calculates the absolute fastest physical route across thousands of independent, interconnected networks. We often talk about data living in the abstract cloud, but every digital action you take is strictly bound by physical geography and the literal speed of light traveling through these cables. Reaching the destination server is only half the battle. Before exchanging any actual files, the two machines must securely agree on how they will communicate. They execute a series of automated introductions. They negotiate TCP, a protocol ensuring reliable data delivery, and TLS, a security protocol encrypting the connection so eavesdroppers cannot intercept data in transit. With a secure line established, your browser finally issues an HTTP request. HTTP, or Hypertext Transfer Protocol, is the application-level demand for the web page's specific files. You might expect the server to fulfill this request by sending the website back as one large, cohesive file. It doesn't. Instead, the server shatters the HTML code, style sheets, and media into thousands of tiny, uniformly sized chunks of data. These chunks are called packets. These small, uniform fragments can navigate a crowded, unpredictable network far more efficiently than a single, bulky file. Those thousands of packets are instantly fired back out onto the physical network, racing towards your screen. They do not travel together. Through packet switching, each individual fragment is sent down an entirely different branching pathway to reach the same endpoint. At every network intersection, intermediate devices called routers process each packet independently. They look at current traffic conditions and instantly divert packets around congested hubs or physically severed cables. It is a lot like how the Statue of Liberty was delivered to the United States. Too large to ship intact, the monument was disassembled, sent across the ocean in hundreds of smaller crates, and delivered with instructions for reassembly. As your computer receives this chaotic barrage of data packets, your browser reads the numbered header instructions stamped on each one and snaps them back into place. Because the data is decentralized and doesn't rely on a single vulnerable pathway, the system automatically routes around damage. If one link fails, the packets simply find another way. The final packet arrives, the code executes, and the web page appears on your screen. Every DNS lookup, ocean crossing, encryption handshake, and packet switch we just tracked happened in less than a single second. What makes this scale of logistics possible is that this massive infrastructure operates entirely without a central control room or a single governing body. Its flawless execution relies on open standards, shared mathematical protocols, and the continuous cooperation of millions of independent networks. The next time a web page loads, you are viewing a globally coordinated choreography, a harmony of physical infrastructure and human cooperation working in perfect sync.